Welcome to the Deep Dive. Today we're strapping in and really going down to the absolute bedrock of computation.
Yeah, the fundamental layer.
Exactly, the lowest level of, well, every device you use.
Yeah.
We're doing a deep dive into digital logic design today. We're really pulling out the core mechanics of how zeros and ones become numbers, yes, but also decisions.
It really is fundamental stuff. We talk a lot about high-level things like AI, machine learning, but everything starts right here. How those simple bits, 0 and 1, how they're structured to mean something. Quantity, sign, logic.
It's the map to the computer's brain, like you said.
Pretty much, yeah. So that's our important today. Extract the essential insights. We'll tackle this in, let's say, 3 main chunks. First up, the basic number system's binary, BCD, hex. The languages computers speak. Then second, we hit that really interesting puzzle. How do you represent negative numbers? We'll look at the standard solution, 2's complement. Ah, yes, crucial stuff.
And finally, we'll explore how logic equations get built and, importantly, how they get simplified. We're talking truth tables and Karnaugh maps.
Making things efficient. Okay, so let's start right at the beginning. The idea of a base, or radix. We all live and breathe base, 10 decimal, right?
10 symbols, 0 through 9.
And we just instinctively get that in a number like, say, 4,200. The 4 means 4 thousands, the 2 means 200s. It's weighted by powers of 10, 103.3, 102.2, and so on.
But computers, they don't see 10 things. They see 2, on, off, 1, 0. That's binary base, too.
Exactly. So instead of powers of 10, the weights are powers of 2. $20, 21, 22, 2.
So if you give me a binary number, let's take that 6-bit example. 0, 100, and 100, and 101. How do I read that?
Well, you just sum the weights for each position where there's a 1.
Yeah.
So it's, let's see, $0 times $32 plus $1 times $16 plus $1 times 88 plus 1 times 4 plus $0 times 2 plus 1 times a 1.
Okay, so 16 plus 8 plus 4 plus 1. That's 29 in decimal.
You got it. And we have names for those positions, too. The one on the far right, the $20 position, that's the least significant bit.
Yeah.
The LSB.
Least impact on the value.
Right. And the one on the far left, the one with the biggest weight, that's the most significant bit, or MSB.
Now, something the sources really emphasize is the fixed bit width. Systems don't just use arbitrary length binary numbers. They commit, like 64 bits in modern CPUs.
That's a critical point. That fixed width, let's call it P bits, defines the entire range of numbers you can represent. For just plain non-negative binary, it goes from 0 all the way up to 2p is 710.
Okay, so the computer's happy with these long strings of zeros and ones, but for us humans...
Oh, it's a nightmare. Try reading a 64-bit number in binary. You'll make mistakes. It's just not practical for communication, which is why we have shorthands. You mentioned 2 key ones, hexadecimal and BCD.
Yeah.
Hexadecimal or hex is base 16. It uses 0 through 9, and then A, B, C, D, E, F for the values 10 through 15.
And the beauty is 16/7 is 204 solars. So 4 binary bits map perfectly to 1 hex digit.
Exactly. It's a brilliant shortcut. You take a long binary string, group it into 4s, starting from the right, the LSB, and replace each group with its hex symbol. Suddenly, a huge binary number becomes a much shorter, manageable hex string.
So like 101.1111111 in binary. Grouping gives 0110101 in binary. That's 7E5. 7E4 to 1 byte in hex. Much cleaner.
Way cleaner. It's purely for human convenience, really. Communicating binary patterns without going cross-eyed.
Okay, so hex is the engineer's friend. What about BCD? Binary coded decimal. That one seems less efficient.
Well, it is in terms of bits used. With BCD, you take each decimal digit separately and convert it to its 4-bit binary form.
So 2021 becomes 2 is 00 sen 00002001. So 0000000000000. That's 16 bits. Normal binary only needed 11 for 2021.
Right. It uses more space. But BCD isn't about saving space. It's about preserving exact decimal representation. Think financial calculations or driving old 7-segment displays that need those distinct decimal digits.
Ah, okay. So it's for specific applications where decimal precision is absolutely paramount, even if it costs more bits.
Precisely. You trade efficiency for that guaranteed decimal fidelity.
Got it. Okay, so that covers positive numbers and 0, natural numbers. But, the world runs on integers, positives, and negatives. How did engineers crack the negative number problem using only 1s and 0s? You can't just put a minus sign on a wire.
No, you can't. And the standard, really universal solution is called the 2's complement form.
2's complement. Heard of it?
It's elegant, but the absolute prerequisite, the first thing you must do, is fix the number of bits, p.
Right, back to the fixed width. And that width immediately sets the range. And it's not symmetrical, is it? For p bits, the range is 2tp1 up to positive 2p1.
Exactly. That asymmetry is key. Let's take 8 bits, a common size.
Okay.
P8. The range is $297,000 to $2,700, says that's Anagers 128 up to positive 127.
So one more negative number than positive.
Yep. The most positive is Neuro 111 on length. That's a $111 one. That's a negative 128 is $100,000. That single extra negative value is sometimes called the singularity.
Okay. And the big advantage, the reason everyone uses this seemingly odd system,
Arithmetic. Specifically, subtraction becomes addition. You don't need separate hardware for subtracting.
how does that work?
Yeah.
The magic property is this. An integer n added to its 2's complement representation, which stands for n, results in 2 p-collars. For example, let's use p6 bits. Take 17, we need to find the pattern for negative 17. Okay, walk me through it. p6, positive 17. That's $16 plus 1, so it's 1,101.
Good. Step 2, find the one's complement. Just
Yeah.
flip every bit. Zeros become ones, become zeros.
So 1,001 becomes under $1,110.
Right.
That's the one's complement. Now, step 3, the final step for 2's complement.
Yeah.
Just add 1, okay? $111.10 plus 1 is $111.
Okay.
So that pattern, $111.1, represents negative 17 in a 6-bit 2's complement system.
That's exactly it. And notice the MSB, the leftmost bit. It's 1.
So the MSB acts like a sign bit, whether for positive, 1 for negative.
Generally, yes. That's a key visual cue. Now, if you add 17, 11, and 11, and 1, or no, not 17, using 6-bit addition.
Let's see. You get $100,000. That's 7 bits. But we're in a 6-bit system.
You're right. The carryout bit, the leftmost one, just gets discarded because there's no place to put it. And what are you left with?
All zeros. Zero. So $70 plus negative 17 equals enevelers. It works. Subtraction is just adding the 2's complement.
Exactly. It simplifies the hardware dramatically.
Yeah.
And converting back is easy, too. If someone gives you $100, you see the MSB is 1, so you know it's negative.
So how do I find out which negative number?
You just apply the same 2's complement process again. Flip the bits of 111 to get on $100, add 1 to get under 500 and honored 1.
Which is positive 17.
Right. So the original pattern, $111 must have been negative 17. It's a perfectly reversible process.
Okay, that's actually quite clever. So we've got numbers sorted, positive and negative, but computers don't just calculate. They need to make decisions, right? Logic.
Absolutely. We need to shift gears from representing quantity to representing truth and making decisions. That brings us to Boolean logic.
Named after George Boole.
The very same. Boolean logic deals with statements that can only be true or false. No middle ground. In digital terms, true is 1, false is 0.
And we have variables, like maybe the state of a switch, which can only be 1 or 0.
Exactly. And we combine these simple true-false variables using basic logical operations, or connectives. The main 3 are A and D, or R, and not.
Right. And a D is usually shown with a dot, like multiplication, or with a plus sign, and not T, usually a bar over the variable.
That's the common notation, yes. Tall bar means not A. And the precise meaning of these operators is defined by something called a truth table.
A truth table just lists out all possible input combinations and the corresponding output for the function.
Correct. For A and D, the output is 1 only if all inputs are 1. If any input is 0, the A and D output is 0.
It's strict, or is more relaxed.
Much more. The OR output is 1 if any input is 1. It's only 0 if all inputs are 0.
And then there's XOR, exclusive OR. That one's a bit different.
Yeah, XOR is true if the inputs are different. So A1, B0 gives 1, A0, B1 gives 1, but A1, B1 gives 0, and A0, B0 also gives 0. True only if one or the other is true, but not both.
Okay, so let's say we design some function we want, maybe checking if 2 bits are equal. We can write out its truth table. How do we get from that table to an actual Boolean equation?
The standard method, especially when starting out, is the sum of products, or SOP form.
Sum of products.
Okay, how does that work?
You look down the output column of your truth table. Find every row where the output is 1.
Okay, focus on the true results.
Right. For each of those rows, you write a product term that's an A and D term. In that term, if an input variable was 1 in that row, you use the variable itself. If the input variable was 0, you use its negated form with the bar.
Ah, okay. So you create an A and D term that is true only for that specific input combination.
Exactly. You do this for every row where the output was 1. Then you simply connect all these individual product terms together with OR operations. That's the sum part of sum of products.
So for that 2-input XOR example, the output is 1 for A0, B1, and for A1, B0.
Right. So the first row, A0, B1, gives the product term bound the bood. The second row, A1, B0, give 1 more.
We OR them together. So 5 star R plus A, AE0, that equation perfectly matches the XOR truth table. Precisely. This SOP method always works. It gives you a valid equation directly from the truth table.
Now, I imagine these equations can get pretty long and complicated if you have more inputs, right?
Yeah.
Lots of product terms ORA'd together.
Oh, absolutely. They can become huge. And in the real world, complexity costs money. It means more gates on the silicon chip, more area, sometimes more power consumption. So simplification is crucial.
How do we simplify them? Are there rules?
Yes, there are fundamental Boolean algebra identities that let us simplify things. De Morgan's theorem is a famous one. It relates AND, or R, and not
Remind me.
over line A plus bar, and also over line A plus B. It lets you convert between A and Ds and ORs when negation is involved. Very useful.
Okay. And what about that other rule you mentioned? The one where a variable just disappears.
Ah, yes, that's based on adjacency. If you have two product terms being ORed, and they are identical except for one variable which is negated in one term and not the other, like $bar plus A plus daybat.
Oh, A is the same, but B changes from Belband to B1.
Right. In that specific case, the variable b becomes irrelevant because the expression is true if a is true, regardless of b's value. So 1a bar b plus ac dot b simplifies down to just $. The b variable drops out completely.
That's a powerful simplification.
It is, but trying to spot all these possible algebraic simplifications, especially with 3 or 4 variables, it gets really tricky just looking at the equation. Your eyes can miss things.
So we need a better way, a visual method.
Exactly. And that's where the Karnaugh map or K-map comes in. It's a graphical tool.
Okay, K-maps. I've seen those grids. How do they help?
A K-map is basically a rearranged truth table. For, say, 3 or 4 variables, you draw a grid. Each cell in the grid corresponds to one unique input combination, one row of the truth table. You fill in the grid with the zeros and ones from your function's output column.
But the grid isn't numbered sequentially, is it? The order seems weird.
That's the genius of it. The rows and columns are ordered using gray code, which means adjacent cells horizontally or vertically differ by only one input variable changing. Even the edges wrap around, so the left edge is adjacent to the right edge and the top to the bottom.
Ah, so it physically places those adjacent terms from the algebra rule next to each other on the map.
Precisely. Now, instead of algebra, you just look for groups of adjacent ones.
Groups? What kind of groups?
You need to circle groups of ones. The groups must be rectangular, and their size must be a power of 2, 2, 4, 8, 16, etc. You want to make each group as large as possible.
So grouping 2 adjacent ones, that corresponds to eliminating one variable, like the dollar bar plus A skill B A war rule.
Exactly. Grouping 4 ones eliminates 2 variables. Grouping 8 eliminates 3. The larger the group, the simpler the resulting term. Okay, so the goal is cover all the ones in the map using the fewest possible groups, making each group as big as you can. That's the game. And remember, wraparound adjacency counts, but diagonal cells are never considered adjacent.
Got it. This sounds way easier than wrestling with algebra.
It is for up to 4 variables, maybe 5 with some effort. It guarantees you'll find the minimal sum of products form.
Now, what about those X's I sometimes see on K-maps? Don't cares.
Ah, yes, don't cares. Those are incredibly useful. A don't care condition arises when a particular input combination either physically can't happen in your system, or if it does happen, you literally don't care what the output is for that specific input.
Like maybe an input from a sensor that can never produce a certain reading?
Exactly.
Yeah.
So on the K-map, you mark those input combinations with an X. Now here's the trick. You can choose to include an X within a group of ones if it helps you make that group larger. So you can treat an X as a 1 if it helps you circle a group of 4 instead of just 2, or 8 instead of just 4.
Precisely.
Right.
But you only use an X if it helps enlarge a group of actual ones. You don't circle groups of just X's. They're only there to help simplify the terms needed to cover the real ones.
That's clever. It gives you extra flexibility for optimization. It can lead to significantly simpler final equations.
Yeah.
So the whole flow becomes clear, right? You start with what you want the circuit to do, maybe described in English.
Then you formalize that into a truth table.
Then you transfer the outputs from the truth table onto a Karnaugh map, including any don't cares.
You circle the largest possible groups of ones, using X's to help, until all ones are covered by the minimum number of groups.
From those groups, you read off the minimized sum of products equation. Each group gives you one simplified product term.
And finally, that minimized equation tells you exactly which logic gates, AND or NIT, you need, and how to connect them to build the actual digital circuit.
That's the complete design flow, from specification to optimized logic. And that reduction, getting from a potentially huge initial equation down to something much smaller, like maybe just SC as in one source example, that's what makes building complex digital hardware practical and affordable.
It really is a journey. We've gone from just figuring out how to write numbers down in binary to the crucial step of handling negative numbers with 2's complement,
Which unified addition and subtraction.
all the way to designing and then drastically simplifying the logic that makes decisions using these visual K-maps. It's quite an intellectual toolkit.
It really underpins everything digital. So, if we were to boil it down, maybe 2 huge takeaways for the listener. First, grasping 2's complement is essential for understanding how computers actually do arithmetic with positive and negative numbers. Absolutely fundamental.
And second, that logic minimization using things like K-maps isn't just academic. It directly translates to saving cost, space, and power in real hardware. Optimization matters.
It really does. And thinking about that simplification, we saw how complex functions built from AND or NOT gates can be simplified. But it goes even further.
How so?
Well, you can actually build all basic logic gates AND, or not using only one type of gate. For instance, the NAND gate. It's called a universal gate.
Wait, you can build everything from just NAND gates?
Everything. ANDs, ORs, not Ts, the whole lot. Okay, that leaves us with a really interesting final thought for you, the listener, to chew on. If you could manufacture silicon chips using only one single type of building block, just millions of identical NAND gates, how might that drastically simplify the entire fabrication process compared to needing distinct processes for ANDs, ORs, and NOT Ts? Think about the implications for mass production.